Today's topic is questions based on given data. So in these problems, you'll generally start with your prompt showing you a table of data, and we'll work from there. So this problem has the table showing the independent variable of time, t, in minutes. That starts at 0 and goes up to 12. And then the dependent variable in the table is r prime of t, feet per minute. So that's a rate of change of feet over time. And that starts at 5.7, and then the numbers decrease from there. The prompt says the volume of a spherical hot air balloon expands as the air inside the balloon is heated. The radius of the balloon in feet is modeled by a twice differentiable function r of time t, where t is measured in minutes. For time values from 0 to 12, the graph of r is concave down. The table above gives selected values of the rate of change, r prime of t, of the radius of the balloon over the time interval from 0 to 12 inclusive. The radius of the balloon is 30 feet when t is equal to 5. Note the volume of a sphere of radius r is given by v equals 4/3 pi r cubed. A. Estimate the radius of the balloon when t equals 5.4 using the tangent line approximation at t equals 5. Is your estimate greater than or less than the true value? Give a reason for your answer. Okay, so whenever we hear tangent line approximation, we know we need to think about the point slope form of a line. And in order to write an equation in point slope form, we need a point and a slope. So we know that the time is 5. And we do have a point given in the problem. The radius of the balloon is 30 feet when t equals 5. So we can use that. Then we're also going to need a slope. The table of values is actually the rate of change of the radius of the balloon over time. So that would be the slope. And at time 5 right here, they tell us that the slope is 2. The rate of change is 2. So normally we go y minus y1 equals m times x minus x1, which is fine. You can do that. However, this problem is really about time for the independent variable and radius for the dependent variable. We're trying to estimate the radius instead of a y value. That'd be an r value. So we might change it to r minus 30 equals 2 times t minus 5. So that is the tangent line approximation for this problem. And now they want us to estimate what r would be given a time value of 5.4. This is a no calculator problem, so they want us to substitute 5.4 in for the time. Oops, I closed my parentheses before I meant to. And we could do add 30 to both sides to get the r by itself. So 5.4 subtract 5 would give us 0.4. Think of that as like 40 cents. Times 2 is 80 cents. Plus 30 is 30.8. And the units would be feet. However, they don't tell you to include units on your answer, so I would not put them down. They will be graded if they are there, and they have to be correct. So there's our approximation for the radius at time 5.4 based on our tangent line approximation. And now we need to say, is this estimate greater than or less than the true value, and give a reason for your answer. You might want to pause the video and ponder that for a moment before I spoil the fun and tell you. But the answer would be greater than, our approximation is greater than the true value, and the reason for that is because the graph of R is concave down. Because R is concave down. I apologize for my handwriting. I am using my finger because my stylus is broken. Okay, so concave down graph would look like this. Anywhere you put a tangent line equation on there, it'll touch the graph and be equal to it there, but any point away from the point of tangency will lie above the curve when it's concave down. So that's the only thing you need for your reasoning. It's concave down. Part B says, find the rate of change of the volume of the balloon with respect to time when t equals 5. Indicate units of measure. Okay, rate of change of volume with respect to time. When you read that, you need to be thinking, what mathematical symbol would represent rate of change, so that's like a derivative, of the volume with respect to time. So that's the derivative of the volume with respect to time. We have a volume equation given right here, the formula for volume of a sphere. So we need to take the derivative of that with respect to the variable time. There is no t in the problem. This is like a related rates problem here. You take the derivative with respect to time, every variable generates a rate. So the left side, v, when you take the derivative, would be dv dt. The right side, you're going to use a power rule. So 3 times 4/3 would just give you 4 pi. Then we subtract 1 from the power, so it'd be r squared, and because we took the derivative of r with respect to time, we multiply by dr dt. And when time is 5, we're supposed to figure out what that is going to equal. Well, there's not really a place to plug in 5 into this equation. However, when time is 5, we know that the radius is 30. That was that point given in the problem. So we can substitute 30 in for the radius, and we know that the rate of change of the radius over time at time 5 is 2, because that is also given in the problem in the table. And then we're going to work this out. So 30 squared would be 900. 4 times 2 is 8. 8 times 900 would be 7,200 pi. Oops, that was supposed to be a pi. We'll just do that again. Okay, and it does say indicate units of measure. So we're changing volume over time. Volume, if the radius is measured in feet, is cubic feet, and the time in this problem is measured in minutes. So 7,200 pi cubic feet per minute was the answer we're looking for there. By the way, I forgot to mention the scoring on part A. Part A was worth 2 points, 1 point for the answer 30.8, and 1 point for saying concave down because, the estimate was greater because it was concave down. So 2 points there. This part is worth 3 points. They give you 2 points for figuring out what dv dt is, and then 1 point for the answer. Moving on to part C. It says use a right-Riemann sum with the 5 subintervals indicated by the data in the table to approximate the integral from 0 to 12 of r prime of t dt. Using correct units, explain the meaning of the integral from 0 to 12 of r prime of t dt in terms of the radius of the balloon. Okay, so starting off with a right Riemann sum. Right Riemann sum means we're finding the areas of rectangles. The first rectangle is going to have a width of 2 because the difference of the first two times 0 and 2 is 2. So it'll be 2 times. Then you choose for a right Riemann sum the y value or the dependent variable value that is on the right side of that interval. So the one with the greater time. So that's going to be 4 plus the next width would be 3 and the next height of the rectangle would be 2. Then we have one that goes from 5 to 7, so that's a width of 2, and then the height would be 1.2, and then the next width is from 7 to 11, which is 4 times the right hand y value 0.6, and finally the last interval would have a width of 1 and then a height of 0.5. So we just work that out. 2 times 4 is 8, 3 times 2 is 6, 2 times 1.2 is 2.4, 4 times 0.6 is 2.4, and 1 times 0.5 is 0.5. And so we add all this together, 14, 15, 16, 17, 18. 18.8 plus 0.5 is 19.3. Okay, so there is our right-hand Riemann sum. Next, using correct units, explain the meaning of the integral from 0 to 12 of r prime of t dt in terms of the radius and the balloon. So, an important acronym that you can use to help you whenever it says to explain the meaning in an AP calculus problem is that you're going to need to include the number. What number are we talking about? The answer to this problem, 19.3. You're going to need to include the units, which in this prompt it actually tells you to include correct units, but guess what? If they had left that off and still said explain the meaning, units would have to be included without that reminder. You need to include time. So the times here are from 0 minutes to 12 minutes. We know that by the upper and lower limits of integration. That needs to be included in the explanation of the meaning. And finally, the situation. What is this problem about? It's not just numbers, it's about a hot air balloon. So it needs to be referenced to the situation, what's going on. So if we're doing 19.3, this was the answer to the integral from 0 to 12 of r prime of t dt. So what we essentially did here was we took the number of minutes and that had passed, we multiplied them by the r prime of t, which was feet per minute, which means feet over minutes. So those minutes would cancel, and the units on this answer would be feet. Remember, it's always a good idea to do the same math to the units that you did to the numbers to figure out what units your answer should be in. So what does that mean exactly? Well, we're going to say from time t equals 0 minutes to time equals 12 minutes, the change in the radius was 19.3 feet. Or I could have said the change in the radius of the spherical hot air balloon. I wanted to be a little bit more precise, but for sure I needed radius in there. So I've talked about the number for the answer, 19.3, I talked about the units on both the time and the answer, feet and minutes. And I've talked about the situation. This is how the radius changed from time 0 to time 12. The radius of the balloon went up 19.3 feet from whatever it started at. Okay. So for part D, it asks us, is your approximation in part C, that integral that we just figured out, greater than or less than the true integral from 0 to 12 of r prime of t dt? Give a reason for your answer. Okay, so we did a right-hand Riemann sum, and we chose the value on the right of each interval. That was the smaller value for each interval. Like for the first interval from 0 to 2, the smaller number is 4. We use that number instead of 5.7. So we would answer that our estimate is going to be less than the true value for the integral from 0 to 12 of r prime of t dt. And the reason is because since r is concave down, r prime, r prime is decreasing. Okay, it's concave down, so we're decreasing. If we're using the number on the right to get the height of each rectangle, then these rectangles are going to fall a little bit less than the curve and not fill it up all the way. So we're going to have gaps, and that means our approximation is going to be a little bit smaller than the true integral. Okay, our next problem is a calculator problem, so you might want to make sure you've got a calculator handy. The table that we are given, our given data, gives us distances in centimeters from 0 to 8, and then temperatures in degrees Celsius starting at 100 and going down to 55. So the prompt says a metal wire of length 8 centimeters is heated at one end. The table above gives selected values of the temperature T of x in degrees Celsius of the wire x centimeters from the heated end. The function T is decreasing and twice differentiable. A. Estimate T prime of 7. Show the work that leads to your answer. Indicate units of measure. Okay, so first let's talk about what the situation even is, what's happening. We have distances and we have temperatures. We've got a wire. Okay, imagine you're holding a wire not with your hand because it's hot, maybe with some pliers or some kind of safety device, and one end of it is being heated. And this table tells us, okay, if you're 0 centimeters from the heated side, so you're like on the heated side, the temperature is 100 degrees. Then as you move down the wire, 1 centimeter, 5 centimeters, 6 centimeters, 8 centimeters away, the temperature is lower as we increase the distance from the heated side. So this is an interesting problem that I like to talk about because normally, most frequently in calculus, the independent variable is time. And in this problem, the independent variable is a distance, so it kind of gives a unique perspective. So part A says estimate T prime of 7. That's the rate of change. Well, we don't have an equation to take a derivative of. All we have are values of a table. So we're estimating it. It says estimate in the problem, so we're just going to use the slope to estimate a rate of change. So we're going to do, we don't even have 7 in the table. We have 6, we have 6 and we have 8. So we're going to use those 2 points, the two closest to it. T of 8 would be y2 minus T of 6 would be y1 over 8 minus 6. So that's going to be 55 minus 62 over 2. And this is a calculator problem, so you're allowed to do that. Negative 7 halves. And it says indicate units of measure. I took two temperatures and subtracted them on the top, so that's degrees Celsius, and I took distances on the bottom, so centimeters on the bottom. Degrees Celsius per centimeter. And that is 1 point just for the answer. Okay, part B says write an integral expression in terms of T of x for the average temperature of the wire. Estimate the average temperature of the wire using the trapezoidal sum with 4 subintervals indicated by the data in the table, and indicate units of measure. Okay, so the first thing we need to do is this integral expression. That means write an integral in terms of T of x for the average temperature of the wire. Average value formula says 1 over b minus a. So that's our final time, 8, well actually not time, centimeters, minus the initial times the integral from 0 to 8 of T of x, whatever we're trying to find the average value of temperature, dx. That gets you 1 point for just writing that down. Then you have to do your trapezoidal sum, which means instead of finding the areas of rectangles here, we're going to find the areas of trapezoids. You must know the formula for the area of a trapezoid on the AP exam. They will not give it to you. 1/2 times base 1 plus base 2 times the height. In this table, it's going to be 1/2 times, we'll say temperature 1 plus temperature 2 times the heights are going to be the differences in consecutive distances in centimeters. So I don't know, should I use x? I guess that's the variable that they use for centimeters here. So we're going to add up how many? 1, 2, 3, 4 trapezoids. Oh, it tells you that, 4 subintervals. Okay. So the first trapezoid would be 1/2 times 100 plus 93 times the difference in centimeters would be 1 plus 1/2 times 93 plus 70 times the difference between 1 and 5 is 4 plus 1/2 times 70 plus 62 times the difference between 5 and 6 is 1. And then finally 1/2 times 62 plus 55 times the difference between 6 and 8 would be 2. And you can pause this video if you want to and calculate that trapezoidal approximation. And that will not be the answer to the problem because they wanted us to use the trapezoidal sum to estimate the average temperature. So that gets you the integral, but not the integral times 1/8. So whatever you get for your answer, you're going to do 1/8 times that value. So I'm going to say this is the area under the curve, and 1/8 times that area will be the answer. So 75.688 would be the answer. And then it says indicate units of measure. This is average temperature. The temperature is in degrees Celsius. So you're going to get 1 point for that integral expression, the 1/8 times the integral from 0 to 8 of T of x. 1 point for showing your work for your trapezoidal sum. Even though this is a calculator problem and you could type that all in, you must write it down on your paper to get credit for that. And then 1 point for the final answer, including correct units. No, I'm wrong. There's a unit point on this for correct units on A, B, and C. So that's weighted separately. Okay, Part C. Find the integral from 0 to 8 of t prime of x dx. Indicate units of measure and explain the meaning of the integral from 0 to 8 of t prime of x dx in terms of the temperature of the wire. Okay, when you do an integral of a derivative, those are like inverse operations and they kind of cancel each other out. So that would be t of x. However, you still have to apply the 8 and the 0 into the result. So that's going to be t of 8 minus t of 0. And what is that? We pull these numbers out of the table. 55 minus 100. So that's going to be negative 45. Indicate units of measure. We just subtracted two temperatures, so degrees Celsius. And then explain the meaning of that integral in terms of the temperature of the wire. So remember, we need to include the number. We need to include the units. We need to include, normally this is time, but for this problem the independent variable is actually distance. So this is kind of why I wanted to do this. It's not always time. Ooh. And then last, S is for situation, which we're talking about heated wire. So what is this? The temperature is 100 degrees on one end. The temperature is 55 degrees on the other end. So the negative 45 degrees Celsius represents the drop in temperature from the heated end of the wire to the other end of the wire. So the temperature drops 45 degrees Celsius from the heated end to the other end of the wire. So number 45, negative is accounted for with the drop. Units for degrees Celsius, I did not include the units for the distance. So from the heated end, which is 0 centimeters from the heat, to the other end, which is 8 centimeters from the heat. But I think that this would probably work the way I've written it without including those units on the time, because it's not, well, it's not time, but we could have done that to be more specific, I suppose. And then the situation is accounted for. So this problem is worth 2 points, one for the value, negative 45, and one for that meaning. Okay, D. Are the data in the table consistent with the assertion that the second derivative of t of x, t double prime of x, is greater than 0, or positive, for every x in the interval from 0 to 8? Explain your answer. Okay, this problem is kind of challenging to do, and it's more work probably than any of the others. So we don't have equations to work with. We are trying to get information about a second derivative when the values in the table are just about the original function. So we're looking at the rate of change of the rate of change of these values. So probably the best way to do that, because we're just given data in a table, is to calculate slopes. So let's calculate some slopes. I'm going to do more work than is necessary to do this problem. We can talk about what would have been required after, but I'm going to go ahead and be thorough in how to do this. So how many slopes can I calculate using the data in this table? 1, 2, 3, 4 total slopes, because I have 4 pairs of consecutive points to work with. So the first slope that I could approximate would be between the first two times or distances in the table. So y2 would be 93 minus y1 would be 100 divided by 1 minus 0. And that would equal negative 7. Then the next one would be 70 minus 93 over 5 minus 1. So that would be negative 23 over 4, which is negative 5.75. Then the next one would be 62 minus 70 over 6 minus 5, which would be negative 8 over 1. And then finally, 55 minus 62 over 8 minus 6 gives us negative 7 over 2, which is negative 3.5. Okay, so how are the derivatives changing over time? If this is true, concave up, positive second derivative, that would mean that these should always be increasing. Are they always increasing? Well, from negative 7 to negative 5.75, it went up because it's less negative, so that's a bigger number. And then from negative 5.75 to negative 8, did it increase? Did the derivative increase? No. Negative 8 is a smaller number than negative 5.75 because it's more negative. So that means that the derivative decreased, which means it had to have been concave down because the rate of change of the rate of change made it something smaller. So we're going to have to say that, let's see, answer the question. Are the data in the table consistent with the assertion that t double prime of x is positive for every x in the interval? The answer to that is no. And the reason is the t prime of x values decrease somewhere between, let's see, this interval started at 1 centimeter, and this one ends at 6 centimeters because this number, negative 8, is smaller than negative 7.5. So, did we actually have to calculate all 4 of those slopes to show this? No, we did not. We had to calculate at least 2 slopes, and it would have needed to show that the rate of change of t prime decreased. It went down somewhere. So as long as we had, say, the 2 interior ones from the table, we could have shown it just using those. All right, that wraps up my little review of questions based on given data. You have a few more problems to practice with and see how those go. Good luck.